Alright, so in this first video we're going to be looking at problem number 71 on page 275. This question is about an integral evaluated from the bounds a to b, and it's finding the area underneath that curve, and it's specifically asking to find what values of a to b make it have the most positive answer. So to start off, we're gonna take a look at the graph of x minus x squared. This helps us visualize our problem. And in this case, x minus x squared is concave down because of a little negative sign there in front of the x squared. You can tell that it's going to cross through 0, 0 because it doesn't have any constants. So we're going to plot that point 0, 0. And then also you can kind of understand that 1 minus 1 squared is going to equal 0, which is going to give us our second 0 on that problem. If you want to do this by factoring out the greatest common factor, if negative x squared plus x equals y, and then you can go ahead and factor on x, which is going to be x, and then negative x plus 1 equals y. So then you can get rid of this x, which is going to give us our 0. So then you're left with negative x plus 1 equals y. Subtract the 1, divide it by negative 1, leaves us with the x equals 1. So we're going to plot that second point over here. We're going to call this 1. Get that second point. This is concave down, so you know everything above here is going to be positive. Points down, then you're left with 0 to 1. Those are going to be our bounds because this whole area is positive, or it's because it's above the x-axis. All these y values are positive, y negative. So then we can finalize our solution here. We can say the integral from 0 to 1 x minus x squared dx gives us our maximum positive value. Alright, so for our second problem here, we're going to be looking at number 72 on page 276. This is another one of those problems that I did in the previous video, where we're going to be maximizing or minimizing an area. This one is asking us to minimize, so I'll just say min there, the equation x to the fourth minus 2x squared, bounded from a to b. So to start off with, like we did in the previous video, we're going to take a look at a little graph of this. I know just based off experience, this is going to do a little curve and then come kind of back up. So we're going to start off on the left side here. It's going to kind of look like a parabola. It's going to flip over and go right back up. So now we can kind of see, if we want to minimize, we want our most negative. So we're going to say most negative. And that's going to be from this bound to this top bound, because everything underneath that is negative. All of this area is negative. Now you're probably asking, what are those bounds? So to do that, or to find that area, we're simply going to factor out and get our zeros for x to the fourth minus 2x squared. So we're going to start off here. We're going to factor out x squared, I believe. So x squared. And then we got x squared minus 2 equals y. X squared is going to, if we were to divide this, we'd have x equals 0 multiplicity of 2. And then we're left with also, so that's that point right there, also x squared minus 2 equals 0. And if we're solving for that, that's going to be x squared equals 2. So then x is equal to plus or minus square root of 2. So that tells you what these points are here. This is negative root 2, and this is positive root 2. So those are our bounds, clearly, because it goes from the most negative to the most positive. So that would be our final answer here. We have the integral from a to b of, a to b being, I'll rewrite that real quick, the integral from negative root 2 to root 2 of x to the fourth minus 2x squared dx. And that right there would be our final answer. Alright, so for problem number 3, we're going to be looking at the equation. I'm going to write number 3 up here. This is number 62 on page 288. We're going to be looking at the equation sine k of x. K in this case is a positive constant as described by the book, so we're going to say pos const equals k. And this k constant is going to be important in this case because it's going to determine our bound of the problem. So this problem is asking us to find that the area underneath one of the humps on the sine graph, which is going to look like that, and k is positive, this area is going to equal 2 over k. So to determine this, we're going to start out by defining our bounds. Like I said earlier, this k is important because for every sine graph, this little k is, it defines how frequent your graph is basically going to cross the x-axis. So if k was equal to 1, this of course would be pi. If k was equal to 2, this would be pi over 2. If k was equal to 3, it'd be pi over 3, so on and so forth. You get the idea. Eventually, this turns into pi over k. So you know, I'll draw this bigger and better here. Bigger and better. It goes like this. This little curve comes up 0 to pi over k. And this area is being determined here. So, because we know that's positive, it's not going to be flipped over. We don't need to worry about that. So we're going to be integrating that real quick. So we have our little integral from 0 to pi over k of sine kx dx. So we're going to take a look at this. We're going to do a quick u sub here. So our u in this case is going to equal kx. We can derive that real quick. So du is equal to k dx. So we're going to divide by that constant. So we're going to throw that out front here. So that's going to turn into 1 over k integral from 0 to pi over k of sine of u. Don't want to forget that nice little du there. Pretty easy integral here, or I should say antiderivative. We're simply going to take the negative cosine variant of that, and for just simplicity's sake, I'm going to plug that back in. So it's going to turn into 1 over k multiplied by the quantity. I'm going to do my big old braces here. This is going to be negative cosine kx minus, and I'm just going to say plus because I know that's going to happen, plus cosine kx, and then this is all in big parentheses here again, integrated from pi over k and 0. Sorry, from 0 to pi over k. So this is just plug and chug at this point, so we're going to have 1 over k out front here. Cosine k of x, those k's are going to cancel, which leaves us with cosine of pi, negative cosine of pi. Cosine of pi, of course, negative 1. So that's going to turn into 1, and then plus cosine, once again, k over x. That k and x is going to cancel. It's going to turn into negative 1. No, it's not. I've done something wrong. Let's take a look at this again real quick. Minus the upper, minus cosine k of x. It's the upper minus the lower. Cosine, that's what I've done. This has to be cosine of 0. My bad. Let me fix that real quick. Cosine of 0, silly me. So cosine of 0 is, of course, 1. And that's going to be plus 1. So this turns into 1 plus 1, which is, of course, 2. This turns into 2 over k. Just like that, you have derived your answer. All right, so this is going to be problem number 4. This is number 65 on page 288. This is a problem asking about the average temperature between time 0 and 25. I'm just going to point those out real quick, 0 and 25. The basic equation for this temperature is 85 minus 3 root 25 minus t. This is just a general equation, not really sure exactly the origins of it, but that doesn't matter because this is math. Part A is pretty simple, so I just went ahead and did that real quick. It just asks you to find the general temperatures for each time. It kind of shows that it's a decreasing trend. The temperature is actually increasing as time goes on. Misspoke there. So part B is where it gets interesting. It says find the average temperature when time is greater than 0 and less than 25. Less than or equal to. Sorry for both of those. I've gone ahead and shown you what this is going to look like in integration form or integral form. This is going to be, and we're going to do this with area. So if you know the graph is going to look something like this. Let's just say it starts from 70, which is up here, goes to 85. So it's going to go up. We'll kind of go with this. So it'll kind of do like this. It'll plateau a little bit because it's a root function. So this area here is going to help us figure out the average. So one nice thing that we know about this is the area has a bunch of y values, but it's just for a given x size. So we're going to call this x0, and all these y values are changing. But what happens when you take the average is it gives you the same area, but it gives you an average line or an average y value. So we're just going to call that, if this is 70 to 85, we're going to go in increments of, would that be 4, 5? Yeah, 5. So we have 1, 2, 3, 4, 5. So it's going to look something like that. This is a little bit small here. I'll try to expand it on this side. So we have our range from 70 to 85. And this is going to be 75, 80, 85. So I guess I was wrong. So it's going to be 2 lines. 75, 80, 85. Yep. So basically what this is going to get is a small line that goes through and has the same area. Obviously, it probably is not going to look like that exactly, but you get the point. And to do this, you're going to multiply by the, you're going to divide by the change in x. So if this area can be represented by x times y, this is the rectangular area. So this is y and this is x. Then you know if you divide the delta x, if you divide all of this changing y values, because these are individual little tiny vertical lines, by your delta x, you're going to get your average y. So I've gone ahead and done this to make this video a little shorter, but this integral from 0 to 25, and this is evaluated from 0 to 25, 85 minus 3 root 25 minus x dx, and that's actually going to give you 1875. That's just a number I got from a calculator, just to help speed this up. And then you're going to multiply, more importantly, divide by your x. So this right here is all of your y values added up, essentially, because they have a width of 0. So then you're going to divide by that x. So we're going to go over 25, because it's your a minus b, b minus a, and that's going to be 25 right there. And that's actually equal to 75. So I'm going to put this over here. 75, I'll do it again down here, but 1875 over 25. 25 will go into 1875 exactly 75 times, which is 75, which is fantastic, because that is right within a range. So that tells us that our average line, if we're looking at this graph again, if it goes up and over, and this is our 25-second mark, and this is our 0-second mark, and this is all of our area, our average temperature will fall right on this line. And that's your answer, 7. All right, so looking at number 5 here. So number 5 asks us to evaluate the differences between using the shell method and using the washer method. So in particular, it's asking us to look at the difference in number of integrals we have to do to complete this problem. So in this problem, it's asking us to revolve this piecewise function around the x-axis. I misspoke, the y-axis. This is a little hourglass shape, what it's going to turn out to look like. It's a very crude drawing, but basically you're going to take this and it's going to sweep around. So you're kind of left with two distinct shapes. It's like a steep bowl at the top and then a flat bottom bowl almost at the bottom, because these graphs are slightly different. So looking at the the graph that we're looking, or the area that we're really looking at is this shaded area, and that's really all we care about. We don't care that it's a bowl or whatever. It's just the area. So you could say it's really like a triangle rotated around. It doesn't really matter. However you look at it, we're going to look at the integrals. So starting off with the washer method, if you're to take the washer method, you actually have to split this up into multiple parts, because you have an upper, which is this x equals 1, and a lower on the bound 1 to 0. So you could say the integral from 0 to 1, and that's your y values, of your upper, which is just 1, so it's going to be 1, minus, and this is all multiplied by pi, mind you, pi minus your lower, and this is all squared. So your upper minus your lower, and this x value is root y. This is all squared. And then this is going to be added to your integral from -1 to 0 of, let's see what that was again, 1 minus your upper minus your lower, which is, in this case, -x to the 4th. If you turn that into x values, it's going to be the 4th root of -y. It's again squared. That pi can go through to these whole things, so I'll put that in a big ol' square bracket. So now that's a big ol' integral you don't want to do. You're going to have to do multiple integrals throughout that whole thing. Not fun, wouldn't recommend it, and also these squares should be on each term, not the whole thing. So I'll fix that real quick. Ignore my bad parentheses, so I'll have a parenthesis here, parenthesis here. You get the gist of it. You wouldn't want to do it this way. Washer method is kind of a niche thing for certain events. Shell method in this case seems pretty superior because you have this clearly defined line that can go all the way and touch both parts of it. So with the shell method, we're going to be left with 2 pi multiplied from, taken from the integral, and you're actually using the x values this time. So, are you? I believe you are. I'll double check at the end of this, but I believe you are. Nonetheless, it's going to be from 0 to 1, and then you're taking your x values, so it's going to be x multiplied by your y values, which in this case is going to be x squared plus, or because it's negative down here, minus x to the 4th. And that's it. And that's one integral. So the shell method in this case is clearly superior. Alright, so now we're looking at problem number 6. This is problem number 39 on page 332 for reference. This problem is very similar to the last problem we just did. It's actually the next problem. We're doing it in backwards order because this one is slightly different for the typical shell method. This one is actually being revolved around the x-axis. So just a small note to difference, or sorry, small difference to note. When you're using the shell method around the x-axis, you're actually having the bounds taken from y values. This is going to be your upper, up, and low. That's for shell method, that is. So that's just a good note. I did figure out that was right. Okay, so now let's get into this problem. So it's basically saying evaluate the difference between shell and washer. In this case, it's going to be a mix between disk and washer because we do have two little parts of it. Nonetheless, I think they're kind of interchangeable because the only difference is in one of them you're subtracting a small portion away. So to start off with, let's look at the disk/washer method. Disk, that's an S, D-I-S-K, /wash, because we can do that. So for the disk and washer method, our radius is going to be our y values. So this is y. So we're going to look at our pi, and then multiplied by the integral, and this is our first portion, 0 to 1, 0 to 1. And this is because it's around the x-axis, remember. 0 to 1, and our radius is going to be this equation here, 3y squared minus 2. 3y squared minus 2 dy. Don't forget that nice little dy. And then we're also going to have, oh, and this is squared, pi r squared, my apologies. Then we're also going to have this little segment over here, and this is integrated, or sorry, yes, again from 0 to 1. So we're going to have another little section on this side, pi 0 to 1, and this is going to be our upper, which is once again going to be our 3y squared minus 2 squared minus our lower value, which is going to be y squared squared dy. And this is a big old integral. We don't like to look at it. It's kind of ugly. It's got a lot of stuff to deal with it. Now we can look at the shell method. Shell, which is just typically nicer for this because we don't have to deal with all of this subtraction. We have one continuous line that we can draw from top to bottom that makes up our shell lines. Again, if we were to reflect this over, I'm going to do this crudely, but it would look something like this, kind of like a rocket ship, and that would be roll sort of shells again. Just as a refresher, if you had this shell here, for instance, it would make a little circle on the bottom and then a circle on the top. And those are what your shells look like because you're expanding slowly. So now look at our shell method. Previously we used the x bounds, but that was around the y-axis. So now we have to use the y bounds because we're revolving around the x-axis. So then we're going to look at this again, taking the integral from 0 to 1. And I think I'm realizing I made a mistake here. This is from -2 to 0, and this is from 0 to 1. My apologies. Just a small difference there because this is our x values, even though we have dy. Okay, continuing on. We have... I lost track. Uh-oh. Oh, no. No, we're good. I changed my mind. I changed it back. That's 0 to 1. I'm getting sidetracked. Continuing on here. 0 to 1, 2 pi, and this is going to be x times our height, which is going to be, again, our y values. But in reality, because it is flip-flopped the other way, we can say a t-flippy, we're going to say y times our x in this case, which is a little bit deceptive, but it really is what it is. And that's going to be the addition of these two. So that's going to be our 3y squared minus 2 plus y squared. And that's going to be multiplied again right there, and that's dy. So once again, one integral, much easier. Quite nice. Alright, so in this next problem we're looking at, this is problem number 7. It's number 85 on page 306 for reference. We're looking at the integral from 0 to 1 of f of x dx. This integral is said to equal 3. So this is just as a refresher, the area underneath the curve generally bound to x or the y-axis. In this case, we're going to say f of x is going to represent the x-axis. So the graph is going to look something like this. It's going to have a little lump, or it's going to be straight, or any of the above. It's going from 0 to 1. So let's call this imaginary line 1. So this shaded region, anything under the C, can be equal to 1. So with that said, the opposite side is going to be either a straight, so if we're looking at this line, a straight shot, or if we were looking at a parabola in that zone. So if we went, say, up like this to 1, then on the other side it would go right back up to 1. I'm going to draw this in a better spot too. So we're going to make a big graph down here. And we're going to describe our end behavior. So we're going to have 1 be down here. 1, 1. And that's a little point. This is an important point, 1, 1 is. Because if we have a straight line, then we have our parabola. It's actually going to dip down a little bit and then come back up and touch it. So a straight line has a power, or is an odd power. So that means that the other side is going to go right down straight like that. But if it's squared like this, it's an even power. So that's actually going to hook right back up to the other side. And it's going to do one of those. And this is going to be, let's say, -1. So this information is useful because if we're looking at f of x here, on the right-hand side, it's equal to 3. So we're going to call this area 3, even though in reality it's not. So it could be an expansion of that. So on the left-hand side, if it's odd, we're going to notice that this area is now on the bottom side. But it's a 180 rotation over the origin because it's odd. So this area is now the same value, but opposite in numeric value. If I said that wrong, correct me in the comments. But basically, if this is 3, this opposite side is going to be -3. And then same goes for the parabola here. If this area that's shaded out under this parabola is reflected over the x-axis, or sorry, y-axis, it is now going to be the same value and the same sign. So I'm going to shade this in over here. This is now 3. So again, we're just going to answer this out. If f of x is odd, then it's going to equal -3. If f of x is even, it's going to equal 3. And that is the general basis of number 85 on the homework. All right, so we're on to problem number 8. Just as reference, this is number 86 on page 306. So in this problem, it is asking us to look at the bounds from negative a to a of the function f of x dx, and it's saying that prove or show that when this function is odd, it is equal to 0. So we're going to go back to this little sketchy graph we have here. We're just going to recap because in the previous problem we showed that when it's 3, the odd function is negative 3 on the other side, so on and so forth. So we're just going to demonstrate this with a little wacky doodle function here. If it comes up and goes over, whatever, an odd function is basically going to be the 180-degree rotation of that same thing. So the area here, per se, let's say from 0 to x, is going to be the inverse of 0 to negative x here, or negative x to 0. So they basically cancel out, because this area comes up as being positive, even though, area can't be positive. So it's going to be the same, but opposite. So let's say this is going to be equal to 8. This would be negative 8. And so they would cancel out. This is just a basic little recap of this. So it's showing A. So then we're going to go on to B and basically do an example of that. So we're going to start out by looking at sine, and we're going to say A is pi over 2. So I'm going to start by drawing my graph, because it's always helpful in these circumstances. And we're going from just a 0 to pi over 2. And this is a sine graph, so sine of 0 is 0, because sine relates to your y values. So it's going to start at 0, and then we're going to go up, and then we're going to go down, and then we're going to go up again to pi over 2. So we're going to put this at pi, and this is pi over 2. And then this is going to be upside down, and then right side up. And this is looking very similar to our previous graph, because this right-hand side is basically reflected 180 degrees upside down. So this positive area is going to be identical to this positive area, as this is going to be identical to this positive area, negative area. And because of this, because we have the same bounds, negative pi over 2 to pi over 2, we can therefore say, and this sine function is essentially a negative power or an odd function. So we're saying the integral from negative pi over 2 to pi over 2 sine of x is equal to 0. That's the basis of it. All right, so this next problem is going to be number 44 on page 324, and this is problem number 9. Look at us go. So this is asking us to evaluate the volume created when you sweep the triangle with these given vertices around the y-axis. So I'll do a little sketch here of what that's going to look like. So we're basically going to have, so it's going to be a tiny little bowl that's triangular on the inside, kind of wacky, but it'll work. Back to the problem at hand. So we have to figure out a way to revolve this, but conventionally we have a rectangle. And I've already kind of done this in problems that you guys have seen, but I haven't really explained how I did that. So the conventional shape that we would sweep if we made this would be just a little cheese wheel. It could be just a disc. So you'd have a center, and then you'd have your ellipse come out, and then it'd be the same on the bottom. It'd just be translated down. It'd be just like that. But then what we got is we cut out this little sector. So it's going to go kind of down there, and then down there, and then that's going to be revolved. So you can kind of fill in the blank the rest of the way around. So you're going to end up with this weird kind of tent shape on the inside of a cylinder. And the way we get this is kind of neat, actually. All it's going to be is the volume of our cheese wheel minus the volume of our tent. So we're going to start out with cheese, because cheese is great. Who doesn't like cheese? So our integral for cheese, and this is on the y-axis, is going to be from 0 to 1, and our equation basically for cheese is 1, because it's just a vertical line. And that's our y value, because the equation for this is x equals 1. Whoops, bumped that. So that's going to be, in parentheses, 1, and this is pi times that squared, and dy. And that's going to be cheese. So this right here is cheese, and then we have minus our tent. Now, tent is a little bit more intimidating, you could say. It's going to be a line with a slope, and we can derive it, I guess, over here if you'd like. Y equals negative x plus 1. Crazy. And we have to make this in terms of y, so we're going to go ahead and do that real quick. It's going to be negative y plus 1 equals x. Because it has to be x values, because that's our radius that we're working in, because this value right here, if you go from this y-axis all the way over, this radius of revolution, so you could kind of imagine an ellipse here, like a little circle, that's on our x-plane, which is kind of hard to illustrate on 2 dimensions, but just kind of keep it in the back of your head that when you're working with the y-axis, radius is going to be x, unless you're doing shell, which we're not talking about. So, continuing on, it's going to be minus the pi times the integral from, again, 0 to 1, same bounds, 0 to 1, except for this time it's going to be y plus 1. You could say 1 minus y. 1 minus y squared, because it's pi r squared, dy. 1 squared is simply going to be 1, so then our integral of that, evaluated from 1 to 0, is going to turn into pi times 1y, because we have to add 1 to our value, or just y. So it's going to be pi y and 1 to 0. We don't care about the 0, we'll get to that later, minus pi. And now this one's a little bit more tricky. You have to do a u sub in it, basically. The u sub is a little bit weird because you don't have nice stuff to cancel out. Doesn't really matter in the long run, so we'll do that real quick. I'll put this off to the side here. So I'll say the indefinite integral of 1 minus y squared dy, and then we'll say u is equal to 1 minus y, du is equal to, dy, du is equal to negative 1, and that's now, dy. Yeah, we're good. dy, so then we divide by negative 1, which is not a big deal. So then we're left with plus, because that negative 1 is going to divide out front, so plus, and then we have the integral from 0 to 1 of u squared, which is a little bit more manageable because we know that power rule. It's very handy. So then we have a little dy there, du, and we can keep going with this. So we can kind of evaluate this real quick, and then I'll put it in. But for now, I'm going to solve this because it's pretty simple. So that's just going to be pi plus, and then we can go back to this. So pi, and then I'm going to start doing my big braces again, or my square brackets, I apologize. This is going to be 1/3 u to the 3, and that's evaluated from 0 to 1. Now we should plug u back in, I apologize. U again we brought over here is 1 minus y, so we'll plug that back in, pi plus pi, and then brackets 1/3 1 minus y cubed, evaluated from 0 to 1. Put our big braces in again, so we got pi plus pi, and then we can start evaluating this. So 1 minus 1 is 0 cubed, is still 0. 1/3 times that is 0, so that's not a big deal. So we got 1 times 0, and then minus our lower bound, plug in our 0. 1 minus 0 is still 1, cubed is 1, times 1/3 is 1/3. So we got 1/3, and this leaves us with pi plus pi over 3. Minus pi over 3. It's pesky negatives, man. Minus pi over 3, which turns into, it's basically 1 minus 1/3, which is 2 pi over 3, which is our handy-dandy cheese wheel. All right, on to our last example. This is going to be number 10. Wrap it all up. This is number 45 on page 324. So in this problem, we're going to be revolving the shape y equals x squared combined with x equals 2 around the y-axis. This is another fun y-axis one. So just as a little precursor, when you're doing y-axis stuff, you got to make sure that your bounds are on that y-axis. All right, so now I'll start this off. I pre-wrote this just because this last one was that was in English. I pre-wrote this so because the last video is a little bit long. So this is from 0 to 4, 2, because that's your outer function right here. This line is 2, so that's going to be covering all of this area. And then minus the sweeped revolution. This is 2 squared, and this is root y squared. Pre-evolution of root y, because that's this smaller area, and I'll shade this in heavily so you kind of get the idea. So basically the area we're left with is this cross-hatch area right here that I'm going to be zoning out. So this is the basis of it. You have the integral pi times the integral of your radius squared. Your radius in this case is 2, minus the pi times your bounds of your integral of your radius, which is root y squared. Nice little thing happens here. We're going to quickly make this all work out. We're going to have pi times the integral 0 to 4 of, 4 dy minus pi times the integral 0 to 4 of y dy. That's quite handy. Something nice that we can add about this is we can kind of combine the two now. So they each have a pi in common, they each have an integral. The only thing they have is a minus, so we can kind of shrink this down to make it pi. Integral from 0 to 4, 4 minus y dy. So that's kind of handy, makes things easier. So then we have pi, and then I'm just going to go ahead and write this out. This turns into 4y minus, and then this is going to turn into 1/2 y squared. And this is, of course, taken from 0 to 4. 0 is going to be nothing, so we can just look at the 4 here. So we have pi times 4 times 4 is 16 minus 1/2 times 16 is 8, which is going to turn into pi times 8, which turns into 8 pi, which is the end of our problem right here.